So we're going to check out a random load cell. Here we have a single point load cell. Looks like it's got a total comp label on it. On the other side, we have a model number. It's a 1040. It's a single point load cell. And look, it gives us a color code. So we have 6 wires on this load cell. Which you could see on the label. Blue and green share the same potential difference, so that's plus excitation and plus sense. Minus sense and minus excitation, brown and black. Signal plus or out, we have red, and signal minus or minus out, we have white. So we have the color code. So we don't have to worry about going through that. So let's apply an excitation voltage to this and also analyze sense. So let's just check it with a meter first. We're going to set the meter in ohms to measure resistance. So with sense and plus excitation, we have blue and green. So if we check the resistance between the two, we should have almost a dead short. 1 ohm. So yes, so those share the same voltage potential. Let us check our other excitation, which is brown and black. So we'll go between brown and black. There we go. 0.7, 0.6 ohms. So basically we have more or less a dead short between the two. So our sense is bonded to our excitation appropriately. It's unusual to have a load cell with sense leads on it, but we have a special case here. So let us so we know our color code. Let's just ohm out our load cell and check if our bridge is balanced. So I'm just going to bend down the senses, our brown and our blue. So we have a green and black excitation, black being negative, and that's on volts. I don't want volts. There we go. So I have 413 ohms across my excitation. Across my signal. I have 350. So this is a 350 ohm load cell. So we're going to go from each of our excitations to each of our signals. And make sure they are the same within plus or minus 3-4 ohms. So 295, 295, 295, 293. So that's within plus or minus 3 ohms. So our bridge looks balanced, our resistance readings look good, and we know the color code. So next we will hook up some excitation. So we have our adjustable power supply. We have 10 volts on our power supply, and we will apply that to our excitation. So our plus excitation is green, so positive DC voltage goes on green. Negative DC voltage goes on black. Again, black is 99 times, or 999,999 times out of 1 million of negative excitation. So we have our excitation applied to our load cell. So we're going to switch our meter to DC millivolts to measure excitation voltage. We don't know what the color code is, but we'll just see what our millivolts look like and if we can assess Whoa. So we have 14.3 millivolts with no load, nothing at all applied to the load cell. So this is telling us that our load cell has been permanently bent. There is a strain gauge inside of the load cell that measures the shear force applied to the load cell. The shear force is permanent, so we have a permanent bend in the load cell. So we are measuring the permanent bend, 14.3 millivolts. So this cell has an unusually high millivolts output. So this load cell is shot.